That's a slightly different period, but you can see there was an awful lot of work going into that to get it up and going in the early days. So as I mentioned, Lawrence Livermore did the ZVol support, but then the rest of the other people from the Linux community really wanted the POSIX interface because the file system's a great thing to have. You don't just want a block interface, and they put the effort into producing the full implementation on Linux. So what's happened to the ZFS code base since it was forked? I'll go through a number of things. This is not a complete list. So the first major thing was we had to work out how to version ZFS. So in the Sun days, there's a linear version number. If you've got version, let's say, it ran up to version 28 at that point. So if you've got version 28, you're kind of supporting everything further back. That's fine when there's one developer producing a linear line of releases. It doesn't work when you've got lots of developers. It doesn't work when you've got something that's not a linear line of releases. It actually didn't work on Solaris because some bug fixes need to be taken back from the Solaris 11 development stream into Solaris 10, and that meant that Solaris 10 got a bit of the dedupe code in there. So yes, you can mount a dedupe file system on Solaris 10 and it sort of works, but that was never, intended. It was just the way things came about because of the linear versioning. All we needed to do is find a way that would cope with lots of different teams, around the world developing features. Some way of identifying these features that wasn't a linear list of version numbers, and then how you put them together when you contribute them into the source base. But also on top of that, you kind of want perhaps a little bit more flexibility about whether a feature is actually enabled or not. So there may be a nice new feature. If you've not used it in your file system, it's quite nice to be able to just take that file system back and mount it on a different platform that doesn't know about that feature. So this has also been built into this new thing called feature flags. So this is now used to version the on-disk format. In OpenZFS, the linear version number is kind of set to 5,000, which is just a big leap ahead of the 28 or the 32, wherever you are, to make sure there's no clash there. But after that point, you look at individual features. So at the bottom here, I picked out some of the features that were in fact, this was SmartOS, current sort of SmartOS download, which is Delphix's implementation. In fact, the first one that went in was a thing called async destroy, so it's a good one to kind of describe how it works. So they changed the way that file systems and or data sets with file systems and ZVols are destroyed because they wanted to do it faster. Well, they wanted better response, faster response to the commands, and actually turned around the way it's done. So when you destroy a file system, kind of the first thing that's done is it's removed from visibility in the tree, and then afterwards it goes through, ZFS goes through asynchronously, kind of destroying the data behind. But that leaves data structures on disk that are different from data structures that would have been there, previous releases of the code. In fact, you might now export or re-import a file system just by rebooting a machine that's got a part destroyed, a Z-pool's got a part destroyed file system on it. And the code kind of needs to know how to do that. So if you want to use that, there's a facility there, and you have to enable this facility called async destroy, which tells ZFS that it's allowed to do this. However, that facility being enabled doesn't actually mean that at that point it's actually in use. So it'll sit there enabled. Now you come along and you destroy a really big file system, a really big ZVol, it's going to take ages. And at that point, the flag gets flipped into a new, gets flipped into an active state, and that kind of indicates that we've now got a layout on the disk that is really using this feature. And if you try and import that pool to a release that doesn't know about this, it's not going to work. Once it's finished destroying the file system, that's not true anymore. So the flag can kind of get flipped back to enabled, which means that we're safe. We can safely kind of read-only mount this on the implementation of the kernel that doesn't know about that particular feature. So that's a sort of example of one of the flags. But they're all independently, no, it's not quite true. Not all completely independent because you have dependencies between them. But on the whole, they're largely independent of each other. So, you know, for example, a new compression algorithm there can be enabled, you know, quite independently of async destroy. You could have the two of them the other way around on different Z pools. That's something you just can't do when you've got a linear version number version in ZFS. So this enables lots of teams to work independently. You see the names of the flags have actually got, you know, something like a DNS name in them. So if somebody else had worked independently and come up with something else that happened to be called async destroy, it'd be identified by a separate DNS name. Having said that, when you actually issue the commands, you generally leave that first part off. So on the whole, I think the aim is to keep these unique, but it enables you to work in an environment where you don't have to be unique globally. You just, you know, within your own domain. So I mentioned LZ4. That's a new compression algorithm that's been incorporated into ZFS. And there are some comparisons here of the different performance of the different compression algorithms around. So LZJB, LZ Jeff Bonwick, was the original compression that was in ZFS. That's the one that Jeff did, you know, in the early days. gzip got added to ZFS somewhat later. Part of the motivation for that was that Grub knows about gzip compressed blocks in file systems. So in theory, you can have you can have a compressed root file system still boot off it. A number of people, particularly from the FreeBSD side, decided that LZ4 was a compression algorithm we ought to have, and actually it's quite obvious when you look at performance comparisons that it does, you know, considerably better than all the other compression algorithms in certain respects. Not quite as good as gzip for compression ratio, but the actual CPU and performance out of it is considerably improved. Higher is better on this. It's considerably better than the others. So that's been in there nearly a year now. And I actually saw some discussions going on yesterday on the IRC channel about somebody who's looking at implementing LZ4HC, which is a higher compression version of LZ4. Comes at higher CPU cost, but you get a better compression ratio out of it. So kind of gives you an example of how people think of things, how it moves on, and how we get better features inside ZFS.
Does it compress better than gzip? It doesn't.
You said it
I'm the
does.
guy who did it.
Oh, was it you? There you go. So another sort of more recent feature. This is an issue that a number of people, particularly with some particular apps, had in ZFS. So if we look at performance that we get out of writing to a ZFS file system, this is basically kind of number of operations at these different lengths of time to write. So what you can see is an enormous number of writes actually go through incredibly quickly, and this is fairly obvious. They're just getting written into memory because, you know, that's faster. You can write to any disk. And then you go up to this end of the scale, and there's a smaller number of writes, but these are taking in fact up to 10 seconds. I'm quite showing that graph clearly. So you've got this kind of idea. If you've got an application that's writing really fast, it's like this man that's kind of doing a hurdle course, except that each hurdle is like a brick wall. So you run as fast as you can, and you hit this brick wall. And you've got to climb over the brick wall as the cache gets emptied out to disk. And then you run as hard as you can again, and then you hit the brick wall. But this brick wall's taking like, you know, up to 10 seconds to climb over. It's not a very nice thing to have some applications. You know, if you've got a progress bar, you've probably seen like progress bars on some operating systems. I'm just copying a file and it goes all the way along, and it's stuck at 99% for the next 10 minutes. It's kind of, you know, a little bit like that scenario. And it doesn't do great things for application performance. If application is actually trying to look at what sort of performance it gets, it's horribly inconsistent. And it actually doesn't help in terms of total IOs through the system, IOs per second. So some work was done to look at this and to actually add something called write throttling. So at the entry point into ZFS from the VFS layer, there's now the ZFS looks at a number of things like the amount of data buffered and kind of what's going on, and it will add 10 microsecond delay, or sorry, 100 microsecond delay at that point. And you think, this is a funny thing to do, because I'm now just deliberately slowing down. But what it actually does to the performance is it takes this line and turns it up the other way. So you've now got a peak where you're actually writing, your application is writing consistently at the speed that the disks at the back end can actually handle. So they're seeing a more realistic performance. You're not running into brick walls as you hurtle down the hurdle course anymore. But the other interesting thing is you actually get better performance out of ZFS by doing this. So it's interesting, you see a little sort of delays, you add a delay there and you actually get better performance because you've now got the application actually matching the speed that back-end ZFS can write to disks. So this is one of the sort of features that I thought I'd talk about in a little bit more detail.
It's a much nicer distribution. Actually, makes sense if you average this out and make a Gaussian distribution. It actually starts to make sense rather than kind of a bad.
Well, yeah, and because the blue one, you've just got, well, let's write to RAM until we hit the brick wall. Now we've got to wait until the RAM's written out to disk. Well, why did you bother? Why did you allow yourself to write to disk hundreds of times faster than you could ever get the data off? I mean, it's all right if it's a short burst, but if it's a continuous stream, then you haven't earned anything. In fact, it's cost you because by matching disk performance, so you're actually getting better throughput through ZFS. I'm not going to go through every new feature, but it's probably worth sort of listing just some of the things that have happened, and this is not a complete list either. So there's some improved rebalancing when you extend a pool. There's a set sort of heuristics used when you add another top-level VDEV to ZFS about how it should use it. And kind of didn't give enough weight to the amount of space in a pool, so that's given a bit more weight and some other things taken into consideration. SCSI unmap over iSCSI when you're serving out iSCSI LUNs. One of the early things was ZPool re-GUID. I know as somebody who spoke to a lot of customers that it's a fairly insignificant thing on the face of it, but actually we had an awful lot of customers that were, needed that feature, particularly people who are using ZFS on top of an enterprise storage array. Actually, let me explain what the problem is there. When you create a pool, there's a unique GUID given to that pool, and ZFS kind of identifies that and uses that as the handle for for handling the pool. If you've got something like an enterprise storage array behind you, you might do something like actually copy that data in the enterprise storage array unknown to ZFS. And then, in fact, a lot of customers do that and then feed that into other systems. For example, getting hold of yesterday's database so that you can kind of have a look at that whilst the database is still continuing to be used elsewhere. I mean, a number of scenarios where that's used. A big problem arises though if you try and bring that pool back into the original system, because it's saying, oh, I've already got that GUID matches. In fact, originally it was even worse than that. ZFS will say, what the hell are all these disks doing with this same GUID? Panic. Okay, it hasn't panicked for a lot. That got fixed quite early on, but basically you wanted to take that copy that you've done and say, right, change the GUID on it so I can bring it back, and it's treated as a completely different Z pool. So that's done. So ZFS has a library called libzfs, which lives in user space and does a lot of the interfacing to commands for, like the ZFS command uses it, Zpool uses it. It's a library that actually, implements a lot of that and implements in the commands into the kernel. It had a horrible interface though. Trying to get errors out of it was quite difficult. Some of the errors actually just got written to std, which is great if you're trying to use it to write a GUI. It doesn't have a std. So libzfs core has been created, ultimately I suspect as a replacement, though they're both still there at the moment, but it's designed to have a nice stable thread-safe programming API. So that tends to be where new features go nowadays. Let's look at time. I won't go through all of these, but another one, I/O queues. So for a long time there was kind of one I/O queue from ZFS into each of the sort of bits of back-end storage. This was interesting because actually we started off by saying this queue can be really big. I think it was like 32 or something, which was actually the limit of one of the versions of SCSI protocol. Trouble is that you could bang like 32 requests down there, and they might all be just things that weren't particularly significant. Then somebody comes along and says, oh, I've got a synchronous I/O request, this is kind of really important for performance, Okay, you can go and join the queue behind the other 32 requests. Well, that wasn't very good.